Bam! Mr. Tarrou. In this calculus lesson, we are going to be learning about alternating series. It's the second time I've flubbed up that word. We've had this condition so far in our studies where, all the terms, or maybe we could exclude the first couple of terms, but basically all the terms in our series had to be positive to be able to talk, say, about the integral test, the p-series test, the direct comparison test, and the limit comparison test. Yeah, they all had the condition that the terms in those series were positive. We may have had a few initial terms that were negative, thus not meeting that condition, but we could disregard maybe a couple, 1, 2, 3 of those initial terms because whether a series converges or diverges is about the behavior of that series as n approaches infinity, not necessarily what's going on with the first couple of terms. We can determine, though, the convergence of a series where not all the terms are positive. And the easiest type of series to deal with, which we'll be working with first, is the alternating series. So we're going to be doing, I'll read this to you, we're going to do 3 examples. We're going to do 2 examples after that of estimating the sum of an alternating series, and then talking about some kind of error from that estimation. And we haven't talked about the sum of a series in quite a while, not since the beginning when we could identify the series as a geometric series, and we've actually been finding the sum of an infinite geometric series since pre-calculus, or if we could set up a telescoping series. Up until now, and actually quite often, we'll be just discussing whether that series converges or diverges, because that's an easier question. So let a sub n be greater than 0. Okay, see, I just said we were going to be talking about alternating series where, and by the way, what that means is if you were to expand that series or set up maybe a partial sum, you'll notice that the terms will go from positive to negative. Anytime you have a negative 1 to a power, we're given 2 alternative forms here, negative 1 to the n and negative 1 to the n plus 1. In an alternating series, either the first and therefore every following sort of odd term, 1, 3, 5, 7, and so on, will be maybe negative, or maybe the second, 4th, 6th, and all those even terms in place, considering the value of n, will be negative. But at any rate, the terms in your sequence will go from, or series will go from positive to negative. Or the sequence is the list of those terms, and the series is when we're adding infinite number of those terms up. But at any rate, we have this condition that a sub n is greater than 0. Well, we're going to kind of separate the a sub n term as one factor, and another factor is going to be that negative 1 to the n, or that negative 1 to the n plus 1 power. This is what's causing the terms to switch back and forth from positive to negative, and we're going to analyze that a sub n term with the idea of that alternating sign removed. So this condition doesn't mean that all the terms in our series is positive. It's just how we're going to evaluate this term that's in the summation symbol. So the alternating series, where, again, we have the summation of from when n goes to 1 to infinity of negative 1 to the n times a sub n, or this alternative form, converges if the following 2 conditions are met. Well, the limit of, as n approaches infinity, of a sub n is equal to 0, that nth term test, which we really should be doing before we start any test for convergence or divergence, because, of course, if the limit of a sub n, whereas n it goes to infinity, is not equal to 0, we're guaranteed the series diverges. Now, we know if that limit is equal to 0, it doesn't guarantee that it converges, like it doesn't like the harmonic series. And then, if you can show that, though, and that a sub n plus 1 is less than or equal to a sub n, so the next term in general terms, the next term in the series is got to be less than or equal to the previous term. So it's like, you're going to, 10, 5, 2.5, and so on, and every number in that series is getting smaller. Now, if you talk about the alternating back and forth between positive and negative values, that idea of getting smaller gets a little convoluted. That's why we're separating that negative 1 to the n sort of off to the side and just looking at a sub n as that positive factor. That just is reading what I said there. Okay, so our first example is not going to be too terribly complicated. I try to pick some interesting examples that you might notice in your homework and maybe over-explain them, but to help you show the math of what's going on. But the first one here is pretty straightforward. Determine the convergence or divergence of the series. Negative 1 to the n plus 1 power. So we have that negative 1 to a power that idea that the terms in our series are going to be alternating back and forth between positive and negative, and we have that familiar 1 over n. We have a p-series with a p-value of 1, or we notice this as the harmonic series, but this is the alternating harmonic series. So just because the harmonic series diverges doesn't necessarily guarantee that this one does. So a little bit weird, but we're going to see here. This is a real standard problem. You'll probably, if you don't have it as an example in your textbook, you'll probably have it as one of your early homework assignments questions. So we have test 1. Is the limit as n approaches infinity of a sub n, or 1 over n, equal to 0? Yeah, if you let n approach infinity, of course, we know that. So now is the second check, is a sub n plus 1 less than or equal to a sub n? Now you have two ways of showing. Now this notation, by the way, with less than or equal to, leaves us open to that, you know, you don't have a, it's basically sort of non-increasing. It's not necessarily decreasing if you have a couple of terms that are equal. Now, overall, the series needs to be basically we need to have the a sub n term decreasing, but you might have a couple of terms, maybe say in the beginning, like the first and second term are equal, and then they start to decrease. So we have two ways of showing that this a sub n term is a decreasing sort of function. With this notation here, is the next term in the series or sequence less than or equal to the previous one? It's a sequence of terms. A series is when you add up all of them. Or you can do the first, find the first derivative and show that the first derivative is negative, which of course, if the first derivative is negative, then you have a monotonic, well, if the first derivative is negative for the entire domain, it's monotonic decreasing, or, with series, we really care about that domain being all positive integers. So is the function decreasing when all your domain values are positive? And I'm going to switch back and forth between those as we go through our examples. With this one, let's just look at this. We have the nth term here. Let's go ahead and plug in n plus 1, and we have 1 over. Now, I'm checking this, right? So I'm not saying that a sub n plus 1 is less than or equal to a sub n. I'm going to, is this the case? I'm going to write it, look at it, analyze it, and then go from there. So we're going to plug in n plus 1, and then we have a sub n, which is n. Well, look, with equal numerators, n plus 1 is larger than n. So with equal numerators, getting that out of the way, this denominator is larger than this denominator. So since n plus 1 is larger than n, then as a fraction, 1 over n plus 1 is definitely going to be less than or equal to 1 over n. So we have satisfied both conditions. Yes, the limit of a sub n is approaching 0, and a sub n plus 1 is less than or equal to a sub n. So with these two checks, we're actually showing that the alternating harmonic series, therefore, converges. And we'll talk more about that later in the lesson coming up, probably the next lesson I post, unless I split this up into two separate parts. But we're going to be talking about how the idea that the harmonic series diverges, but the alternating harmonic series converges. That's going to be discussion about absolute convergence and conditional convergence. But that is the end of our first example. Let's get on to something a little bit more interesting. For our second example, we have the series of -1 to the n plus 1 power times the natural log of n plus 2 over n plus 2. Okay, it's a little bit more complicated. We are going to test whether or not this alternating series, right there, -1 to a power, that alternating series is going to converge or diverge. So the first test one more time, or the condition that needs to be met for that that conclusion that the alternating series converges is that the limit as n approaches infinity of a sub n is equal to 0. And really, that's just the nth term test. I hope it's equal to 0, otherwise this example is going to be done really quick. Okay, so we have a limit in determinate form. Hopefully by now we're very comfortable with L'Hopital's rule. I just like to pick the examples that are super straightforward because, you know, we'll probably have some easy examples in your textbook. So we're going to take the derivative of the numerator and denominator separately. Great. So when we take the derivative of the natural log, that's going to be, of course, u prime over u. And if you're taking the derivative with respect to n anyway, that's going to be 1 over n plus 2. Same thing here. The derivative of a single degree term is simply going to be 1. And now we have 1 over n plus 2, letting n go to infinity. We get 0. So we've passed the first condition. The second condition is a sub n plus 1 less than or equal to a sub n. Now really, when you write this, we really want to make sure that this is basically like a decreasing series. But maybe your first and your second term are the same, and then they kind of start to fall after that. So that's why we have this kind of the door opened up here that that a sub n plus 1 is less than or equal to a sub n. Overall, we do want that series to be decreasing. Oh, I'm taking such a long pause, excuse me. The terms in that series to be decreasing, but we want to leave that open possibility of maybe the first two terms are equal and then it starts to fall, something like that. So is this true? Is this a decreasing function? And instead of, with this natural log notation, doing a substitution of n plus 1 and comparing it to just n, let's go ahead and this time say let f of x equal the natural log of x plus 2 over x plus 2. And we're setting up a different function because the domain of these series and sequences, of course, are all positive integers. You can't take a derivative of a discrete function. It needs to be a continuous function. So we're just going to kind of do that off to the side and solve and satisfy that legality, if you will, of being able to take a derivative. So then f prime of x is low d high minus high d low all over low low. Now we need to find out for what values of x is this first derivative negative, because we want this, we can't force this to be a decreasing function, but we're just testing whether or not it's a decreasing function. And where is it decreasing? Are we going to maybe have to eliminate the first couple of terms in the series to satisfy these two conditions, or maybe we're just good to go? So we're going to have the x plus 2 and the x plus 2 cancel out. And with that denominator always being positive, we just need to find out if anything is going to make the numerator of this first derivative positive, or is it always going to be negative? Okay. Well, I'm going from exact format to an approximation, but e is approximately 2.718, subtracting from 2, and x needs to be greater than, 0.718 approximately. And if that happens to be the case, then the numerator of our derivative is going to be negative, and if our first derivative is negative, we've justified that we have a decreasing function, that a sub n plus 1 is going to be less than or equal to a sub n, not x, when n is greater than or equal to 1. So the limit of a sub n as n approaches infinity is 0. Yes, every term in our series is going to be less than or equal to the previous term. So basically, we have a decreasing idea with all of our terms. And because these two conditions pass, the given alternating series converges. On to our last example, number 3, right now. Bang! No, 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 no. For our last example, I want to give you a little bit of, I want to go off track here just a little bit before we finish this, this third example. I am basically relearning calculus just to make these videos for you guys out in YouTube. I have a bachelor's of science in mathematics, and I have been teaching at my high school for 20 years, but and I love teaching, right? That's why I'm making these videos for YouTube, right? And I got to teach calculus for the first time 3 years ago, and it felt awesome, you know, not only kind of putting myself back to school to relearn those old skills, to prepare to teach my class, and thankfully it's been just absolutely awesome, but then, you know, extend these lessons on to you guys. Well, that curriculum is done now. I'm really, you know, I don't teach Calculus 2 at my high school, and I don't teach Calculus BC. This is just for you guys. And especially as you know, you're in calculus, the book and even the solutions guide sometimes is really sketchy on the amount of work that they're showing to validate the answers that they're getting. And as I present these lessons for you all, I am not going to teach, you know, concepts and problems, of course, that I don't feel 100% confident, for my understanding of how those problems are working. So honestly, sometimes I don't make or include certain types of questions, like, you know, I do proofs when I can, but, you know, at any rate, I want to make sure that we completely comprehend what's going on with this problem, because I was a little bit sketchy when I looked at the solutions guide. I went online and I found similar help for similar types of problems, and honestly, those solutions seemed even thinner or even more sort of like, well, the answer is just obvious. In case it's not obvious to you, we're going to make sure that we completely understand why this alternating series is converging. And probably a little bit overkill in the amount of work that we're going to show, but I hope it helps you understand what's actually going on. So the limit as n approaches infinity, sometimes as teachers, you know, we just say, well, it's just obvious, or that's just a fact, or you should know that, or whatever, and then you're like, but I don't. So in case you feel like that with this question, you know, I would say that I hope I'm a good math teacher, but I am not a mathematician. And sometimes I need a little bit of extra explanation myself. So is the limit of a sub n actually equal to 0? I mean, I've never seen an a sub n term like this, or, you know, just talking out loud. And it seems like it should be 0. I mean, and maybe this is too obvious to over-explain this, but each of these factors in the denominator, yeah, they look to be less than every corresponding factor in the numerator. And indeed, 4n minus 3, if we're talking about a very large n, should be greater than 3n minus 2. So it does seem like the denominator is growing faster than the numerator, thus the limit is going to be equal to 0. But can we really, like, in a more like obvious way, validate that it actually is equal to 0? We can pull a factor out of the numerator and a factor out of the denominator, and I think show the fact that the limit here is equal to 0 a bit more obvious. Okay, did you see what I did there? I took that factor 4 and pulled it out front, of course, sort of, and so I pushed over the 7, and these factors are getting bigger by 3, of course, so 7 plus 3 is equal to 10. And I originally had n terms in the numerator and factors in the denominator. I want to keep the number of those factors the same. So if I took one of the factors out of the numerator, I want to take one of the factors out of the denominator. Now I don't want to take out a factor of 5. I'm trying to make it obvious that the limit of this expression is equal to 0. So I'm going to take out the 4n minus 3. Now, what is the factor just before this factor? If this is the nth term, what is the n minus 1 term? Okay, so it's 1 times 5 times 9 times something, 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 times 4n minus 7, and then 4n minus 3. Now, if I've taken that factor of 4n minus 3 and pulled it out here, then this now last factor is going to be 4n minus 7. Now, what's the limit of that? The limit of 4 as n approaches infinity is 4. The limit of all of this, now, I don't necessarily, well, maybe we do understand, maybe we can just see the limit as n approaches infinity is 0. But we have a matching factors of 1, then we have matching, we have these factors of 7 and 9. Now 7's bigger than 5 and 10's a little bit bigger than 9. But on the numerator, we're adding by 4 to get these consecutive factors. Down here, we're adding by 4. Did I say 4? We're adding by 3, we're adding by 4. So at some point, the factors, the matching factors in the denominator are going to be larger than the numerator. And we already had the idea that maybe this was approaching 0. We're just not positive about it. But as we let n approach infinity of 1 over 4n minus 3, now that is 1 over infinity. And that is definitely going to be 0. Now, I can't just say that anything times 0 is equal to 0 because infinity times 0 is a form of an indeterminate. And, you know, we saw that when we were learning L'Hopital's rule. But we're pretty confident that this is not approaching infinity. And I'm just trying to make it a bit more obvious that, yes, the limit of a sub n as n approaches infinity definitely is indeed equal to 0. So we have passed our first check. Now the second condition, and this is going to be a little bit of writing. I might be able to squeeze it into a couple of lines. I'm going to go ahead and erase this, as I think I might run out of room. Is a sub n plus 1 less than or equal to a sub n? I'm not going to obviously try and find a derivative of this crazy thing, so we're going to plug in a sub n plus, or plug in that n plus 1 expression to find the next term here. Okay. We're looking to verify, check, that a sub n plus 1 is less than or equal to a sub n. Well, here's what a sub n plus 1 looks like, and here's what a sub n looks like. Let me clean this up just a little bit. Okay. Now, when comparing fractions, if we can make the numerator, well, normally, you know, we want to make, sometimes we can look at the numerator and then compare the denominator, or a lot of times we make the denominators equal and then compare the numerators to determine which fraction is larger. So this multiplications goes all the way out to the sort of n plus 1 term. So like if this is n plus 1 and I say, well, what's the nth term? I'm just going to write 4n minus 3. So I'm going to come over here and I'm going to multiply the numerator and denominator, except that you probably aren't going to be able to see that read very well. Now, if I can make the denominators match, if I can get the denominators to match, I can just focus on the numerators. Okay, let's see here. So we've got what was before this? If this was the n plus 1 term, then the nth term, I believe, is supposed to be 3n minus 2. Right? Oh yeah, that's right. This is the nth term, and we just plugged in n plus 1. So yeah, that's the n plus 1 term, factor. And this is the nth factor. Now if we look at it that way, and remembering, of course, that we have an inequality, right? If you multiply or divide by a negative number on both sides of an inequality, you're going to change the direction of the sign, but the domain of your, well, not, forget I just said that. We've got 1, 4, 7, all of these factors are going to be positive, and indeed n, you know, the domain here that we're going to plug into the series is all positive integers. So 3 times a positive value minus 2, basically 3 times positive infinity minus 2, all these factors are going to be positive. So we're going to divide both sides of this inequality and cancel out the 1, 4, 7, so on and so on up to the 3n minus 2, and we don't need to worry about changing that inequality sign. And we have is 3n plus 1 less than or equal to 4n plus 1, keeping in mind that n starts at 1 and goes to infinity, so n is positive. So indeed, with the plus 1 on both sides, we can really subtract both sides by 1, and we have, 3n, 3 times some number compared to 4 times that same number plus 1. We have shown that 3n plus 1 is guaranteed to be less. Okay, I think I was just about to say that we have enough, we've passed both conditions, therefore the alternating series converges. Now, we've had our 3 examples showing how maybe these alternating series converge or diverge. Actually, all 3 of these examples converged. Hopefully you're okay with that. And but what about if they do converge? How can we estimate the series with just a partial sum? Well, that's coming up right now. So we are going to be talking about the alternating series remainder. Let's estimate the sum of that series. If a convergent alternating series satisfies the condition of a sub n plus 1 is less than or equal to a sub n, then the absolute value of the remainder r sub n involved in approximating the sum s by, that's the sum of the series, by the s sub n partial sum is less than or equal to the first neglected term, or in other words, the absolute value of s minus s sub n is equal to the absolute value of r sub n, which is guaranteed to be less than or equal to a sub n plus 1. I said there was actually going to be 2 examples, but I want to kind of explain what all these words mean and show you it working through a series that we can easily find the infinite geometric series. So we have this summation where n starts at 1 and goes to infinity of negative 1/2 to the n minus 1 power. And if we expand this series out, letting n be 1 and 2 and 3, 4, so on and so on. Well, let's see here. When n is 1, we're going to have negative 1/2 to the 0 power, which is 1. When n is 2, we have 2 minus 1, which is 1. And we have negative 1/2 raised to the 1 power, which is going to be negative 1/2, and so on and so on. Okay, now if we expand this on, we could expand this on to the nth term, and then, that's just going to continue to go on forever. Okay. So what is the sum? What is the infinite sum? And all of this, now I'm looking at this and I've kind of got it up too close to the top of the board. So let me take out these counting values of n and just say that this whole expansion, of course, is s, okay? Now, normally, it's very difficult to find out the sum of the series, but since this is geometric and we have r, which is equal to negative 1/2, and our geometric series of course converge when the absolute value of r is less than 1, we have that the series is equal to the first term, a, as our book calls it. Your pre-calc book would have said a sub 1 just to indicate the first term in the series, over 1 minus r. So we have 1 over 1 minus that r value of negative 1/2, and that's 2/3. So as we add these values, we have 1 minus 1/2 is 1/2, and now we've got 1/2 plus 1/4 is 3/4, now minus 1/8 plus 1/16, and so on and so on and so on, forever and ever. The sum of that series is going to be equal to 2/3. Well, the idea of this alternating series remainder idea is that we're going to be able to estimate the sum of the series by a partial sum. So, Let's see, do I have that written right now? Yeah. Positive, negative, okay. Good. Sorry about the mistake. I don't know how long you're probably screaming through the camera. Hello, you didn't alternate the sign. So we have S of 1, 2, 3, 4, 5, 6, 7. All right, 1, 2, 3, 4, 5, 6, 7. Now, just to make sure my notes jive, yeah, because I wanted to find a partial sum. And I'm not sure exactly why I decided to find the sum of the first 7, but that is a partial sum, in this case S sub 7, and S sub 7, right off the top of my head, is going to be equal to 0.6718. Okay, so because of this nice, neat formula that we were given again in calculus and initially in pre-calculus, and maybe even algebra 2, we know that the series is equal to 2/3, or that the series is, the infinite sum is approximately 0.6667. Actually, it's 0.6 repeating, right? Now check this out. We've only added the first 7 terms of the series, a partial sum based off the first 7 terms. And the absolute value of 0.6667 minus 0.6718 is, right off the top of my head, going to be, looking at the absolute value, the remainder, basically how far off is the partial sum from the sum of the infinite series. And that is going to be 0.0051. Now, this says that the absolute value of the remainder involved in approximating the sum, the infinite sum S, or the series, by S sub n, the partial sum, is less than or equal to the first neglected term. Well, our first neglected term, kind of separating the idea of the plus minus, the alternating sign with the a sub n terms, a sub n, a sub 8, this is supposed to be less than or equal to a sub 8. Now, why am I picking a sub 8? Because we've looked at a partial sum of 7 terms. So we've already worked through the first 7. And we're going to compare the remainder, how far off we are comparing the series, the infinite sum to the partial sum, is less than or equal to the first neglected term. We've added the first 7. The first term that we did not include in our partial sum, that neglected term, is 1/28. Well, a sub 8, or 1/128, is approximately equal to 0.0078. So with a nice little concrete example, we have shown that when you take a partial sum, that the remainder, the difference between the series and the partial sum, is always going to be less than that sort of the first term that's in the rest of the neglected terms. And by the way, where is this, I've highlighted that this never-ending summation of terms, is all of this expression that I've written with the plus going through the n, alternating the signs on for whatever. Here's the partial sum, or S sub n. This is S minus S sub n. And the absolute value for the sum of all of these terms is always going to be less than that first term that's sort of in this remainder, that first neglected term. And okay, so this is like 1/28, and I don't have any more terms beyond here. So let's pretend for a second, even though I don't know why I didn't do this in the first place. What if we just use the first 2 terms in this series to estimate the partial sum of the first 2 terms, using the first 2 terms, to estimate the series? Well, the sum of the series, that's going to be 1 minus 1/2. So just looking at the first 2 terms, we're estimating the sum of the series to be 0.5 when it's actually indeed 0.666, and so on and so on. Well, look at the first that would make that from positive 1/4 minus 1/8 plus 6, that'd make the rest of this all the remainder, the s minus s sub n. And the first neglected term would be 1/4. Well, what happens after that? You're going to take and subtract 1/8. Well, now you're down to what? 2/8 minus an eighth is an eighth. And then you add a 16th, and then you subtract, and then you add. If your first term is 1/4, and then you subtract by basically half of that, and you're down to 1/8, then if you add by a 16th, you're adding by smaller values. This is basically like a, a sub n plus 1 is less than or equal to a sub n. This is a decreasing series. You're never going to, you're always adding by a smaller number. Like you've taken this 1/4, you've subtracted sort of effectively half of that, and then you're adding by less than that half, and then you're subtracting again. You're never going to get back up to a value greater than that 1/4. And so that's what's going on here with the alternating series remainder. It actually doesn't take sometimes a very big partial sum to estimate the sum of the series, quite well. So we're going to do one example of just coming up with an estimated value for the series, and then, let's set some parameters. Let's say, that we want to estimate the sum of the series within, a certain margin of error. How many terms would we have to include in our partial sum to get within that acceptable margin of error? That's going to be that's going to be our last two examples. Bam! Alrighty, we are going to estimate the sum of the series by using the first 6 terms, not 7 like the last time. And our series here, we have -1 to the n plus 1 power times 5 over n cubed. And expanding this out just to see what this is going to look like, we have, well, let's write this. That's what we're doing anyway. S sub 6. What is that going to be equal to? That is going to be, well, the first term. Let's let n equal 1. We have 1 plus 1, which is 2. -1 squared is positive. And we have, let's do a little darker up here, 1. So we have 5 to the 1 cubed, which is 1. Okay. N equal 2. 2 plus 1 is 3. -1 to the third power is -1. And then we've got 5 over 2 cubed, which is 8. Okay, so let's just expand this out a little bit quicker. Okay, so we have our first 6 terms, our partial sum written out. Now, if you, of course, I'm just going to put this in a calculator. S sub 6 is going to be equal to, or we're going to be rounded off, approximately equal to 4.499. Now, we know that that is not the sum of the series. It's only the partial sum. It's estimating the sum of the series. Now, that estimate kind of has a margin of error, right? And can we give a range of values that represent, where the sum of the series might actually be? Well, over here we have the absolute value of S, that's the sum of the series we don't know, minus 4.499 is, of course, that remainder, and that remainder has to be less than or equal to a sub n plus 1. Okay, well, what's a sub n plus 1? We've added up the first 6 terms, so what's a sub 7? Well, a sub 7, 7 plus 1 is 8. -1 to the 8th power, any even power is positive. We have 5 over 7 to the 3rd power, and that's going to be 5, and I don't really want to take the time to do 49 times 7 in my head, because you probably want to see another example and not have this video go on forever. 343. Now, 5 over 343 is approximately equal to, again, right off the top of my head, 0.0146. I wrote equal because I was going to say that this was equal to the absolute value of r sub n, but that's less than or equal to a sub n, so I need that inequality in there. So that is our a sub 7th term, the first neglected term. And now rewriting this so that we don't have an absolute value symbol, we have negative 0.0146 is less than or equal to s minus 4.499 is less than or equal to 0.0146. Adding 4.499 to both sides, we get that s is greater than or equal to 4.4844 and less than or equal to 4.5136. So by just adding the first 6 terms of the series, we know that our remainder, that we're off by no more than 0.0146 units. And so ultimately, that gives us a range of values for the sum of the series, the sum of an infinite number of terms. By just looking at the first 6, that the sum of the series is somewhere between, 4.48 and 4.513. Now, what if I required you to estimate the sum of the series within a given margin of error? That's our last example. Bam! It's the last example determining the number of terms required to approximate the sum of the series with an error of less than 0.001. And our series over here is negative 1 to the n power over 3 times n cubed minus 2. Now we don't know what the sum of the series is, and there's not an easy formula to identify that. So we're going to estimate it with a partial sum. And we're going to come down here and remind ourselves that the absolute value of s minus s sub n is equal to the absolute value of r sub n, that error, that remainder, which is going to be guaranteed to be less than or equal to a sub n plus 1. Now I want to have that error, that remainder, to be less than, I want this to be less than 0.001, which in turn is less than or equal to a sub n plus 1. Now if I look at this and tried to figure out how many terms I'm going to need by comparing the series, the sum of the series with the partial sum, how am I going to do that? There's 2 unknowns here. I don't know what either one of these are. I can't solve an inequality with 2 unknowns in it. So we're going to attack this situation, this idea, this problem with working with just the a sub n term, or just the a sub n plus 1 term. If the difference between the series and the partial sum is my remainder, my error, and I want that error to be less than 0.001, which is guaranteed then by this alternating series remainder fact, theorem, whatever we got here you want to call it, that 0.001 is always going to be, the remainder is always going to be less than or equal to the first neglected term, the a sub n plus 1 term. Well, if I just say, well, we're going to make a sub n plus 1 less than 0.001, if I force my a sub n plus 1 term to be less than the maximum error that I'm going to allow, then by default, the difference between the series and the partial sum is guaranteed to be less than 0.001. Do you get this? This remainder, this is the remainder I want it less than 0.001, which by the alternating series remainder theorem is less than a sub n plus s, less than or equal to a sub n plus 1. But if I make a sub n plus 1 less than 0.001, well, that first neglected term is bigger than a remainder. But if I make that term less than the error that we're allowing, then I'm guaranteed an n such that when I find the partial sum and I subtract it from the sum of the difference, I subtract it from the sum of the series, I'm going to get an error which is guaranteed to be less than 0.001. So a sub n plus 1, what's that term going to look like? Well, that is going to look like, remember, a sub n has to be greater than or equal to greater than 0. We're sort of moving that alternating idea that negative 1 to the n off to the side, and our a sub n is 1 over. Now a sub n plus 1 is going to be 1 over 3 times n plus 1 raised to the third power minus 2, and I want that a sub n plus 1 term to be less than 0.001. Okay, now all I have to do is solve this for n. We're going to multiply both sides by 3 times n plus 1 cubed minus 2. Divide both sides by 0.001, and we get 1,000 is less than 3 times n plus 1 cubed minus 2. Add 2 to both sides, we get 1,002 is less than 3 times n plus 1 cubed. Divide both sides by 3. And let's see here, there's 3 3s in 10. Remainder of 1. Another 3 3s in that 10. Remainder of 1. And we got 12, and there's 4 3s in 12. So 342 is less than n plus 1 cubed. Now cube and root both sides, and doing this not right off the top of my head. Cube rooting both sides, we get that 6.94 is less than n plus 1. And I'm running a little bit out of room because I have the screen board in the way. But subtracting 1 from both sides, we have 5.94 is less than n, so n is going to be equal to 6. If I use an n value of 6, I'm guaranteeing that the difference between the series, the sum of the series, and the partial sum is going to be less than this maximum allowable error of 0.001. Now, if you look back at my series, my lower limit of 0. So if I talk about finding a partial sum where n starts at 0 and goes up to 6, that's actually saying, and again, a lot of your problems, you will have some questions in your homework where this lower limit is 0. A lot of times it's going to be, a standard sort of, if you will, lower limit of 1. But if my lower limit is 0 here, and I'm saying that to guarantee, at least with this process, we're saying that we need at least, we need n to be 6, then actually that means that we're going to be working with a partial sum of 7 terms. And that is the end of my last example. I'm Mr. True. Bam! Go do your homework.